What is Blackbody radiation? When we extend thermodynamic analysis, we learn that there are three modes of heat transfer: conduction, which occur through a solid or a stationary fluid; convection, from a surface to a moving fluid; and radiation, energy emitted by every matter that is at non-zero temperature. Transported by electromagnetic waves or alternatively photons, radiation doesn't require the presence of material medium. In fact, it occurs more efficiently in vacuum. Without radiation, life on Earth wouldn't be possible, because this is the only way to receive energy from the sun. We already know that radiation depends on temperature, but how measure that if every material has different emission, absorption, reflection, and transmission? Well, this problem was solved introducing the concept of a theoretical object, called blackbody. A blackbody absorbs and emits all incident radiation, regardless of wavelength and direction. It's a diffuse emitter, and for a prescribed temperature and wavelength, no surface can emit more energy than a blackbody. As the perfect absorber and emitter, the blackbody serves as a standard against which the radiative properties of actual surfaces may be compared. Although no surface has precisely the properties of a blackbody, the closest approximation is achieved by a cavity whose inner surface is at a uniform temperature. Defined blackbody, we can now study radiation properties of materials as emissive power, rate at which radiation is emitted from a surface per unit area, and it's prescribed by this equation, where Ts is the absolute temperature of the surface and sigma is the Stefan-Boltzmann constant. Epsilon represents emissivity, a number with values in the range 0 to 1. This property provides a measure of how efficiently a surface emits energy relative to a blackbody, whose emissivity equals 1. Emissive power can be also analyzed by its intensity emitted at the wavelength, as shown in the graph of spectral distribution of Planck's law. Here we have wavelength of ultraviolet waves, visible band emission, and infrared wavelength. The lines represent constant temperatures. According to Wien's displacement law, the maximum spectral emissive power is displaced to shorter wavelengths with increasing temperature. Since the Sun emits approximately as a blackbody at 5800 K, its greatest emission is in the middle of the visible spectrum, almost 0.5 micrometers. Then it makes the Sun appear yellow to ice. But materials on Earth have lower temperature, so we usually can't see radiation emitted from them, with few exceptions such as light bulbs and lava. Then, scientists have created the infrared camera, device that forms an image using signs of infrared radiation and converting them to an image using visible light. Thermography is used in a lot of applications, as night vision, search and rescue, energy auditing of building insulation, detection of refrigerant leaks, flame detector, and many others. For more information, read the Chapter 12 from Incropera's book, Fundamentals of Heat and Mass Transfer, 7th edition. Thank you for watching.